So a new topic of discussion today is called modular arithmetic. That may be a completely new term to you. I will discuss the meaning of that term in a moment, but I have some background information to start us off and kind of get us built up to that idea. So the first thing is this definition here of what we call relatively prime, okay? We know what prime numbers are, right? Prime numbers are numbers that have only two divisors, two distinct divisors, right? Namely 1 itself. Here we have two numbers that are relatively prime. And of course, they should be natural numbers. Relatively prime if their greatest common divisor is 1, okay? So in other words, if I gave you a list of some options here, things like 6 and 10 are not relatively prime because their greatest common divisor is 2, right? They have a divisor other than 1. So the GCD of 6 and 10 is equal to 2, so they're not relatively prime, okay? Something like, let's see, how about maybe 9 and 14 are relatively prime. Okay, 9 and 14. And so if you think about the factors of 9 splits up into 3 and 3. Well, actually, rather than doing a factor tree, you should probably look at the actual factors. Factors of 9 are 1 and 9, 3 and 3, right? That's all of them, or the divisors. The divisors of 14 are 1 and 14, 2 and 7. Out of this whole list, the only thing common is the number 1, so the GCD for 9 and 14 is 1. Okay? Therefore, they are relatively prime. Now, neither one of these numbers is prime itself. The numbers don't have to be prime. They just have to share the number 1 as a factor only. Okay? Okay, so that's just a definition of relatively prime. And this is going to be a really interesting idea because numbers that are relatively prime have some very important or create very important patterns in relationships. Okay. Now, this idea of modular arithmetic is important. You guys have probably all seen a 12-hour clock, right? I'm guessing. 12-hour clock, of course, is just a circle. That's not too bad. With the numbers 1 through 12 listed around the circle in a clockwise direction, right? So you have 12 up on top, you have 6 on the bottom, 3, 9 on the right and left, and in between you have 1, 2, here you have 4 and 5, here you have 7 and 8, and here you'd have 10 and 11. Okay, so this would be our 12-hour clock. Now, what's interesting about time, if we think about it in terms of 12 hours, and you could think of it in terms of 24 or military time, or it doesn't matter really. For the example, you can use 12 because it's just easier to write 12 than 24. But when you get, if you get around to, let's say, 8 o'clock, right, you have your hour hand is at 8 o'clock then, and you wanted to add, let's say, 5 hours to that. Well, if you added 5 to 8, most of us think of 8 plus 5 as 13, right? But when we're dealing with clock arithmetic or modular arithmetic, clock arithmetic is kind of a, I don't know, it's kind of a popular name for this, but modular arithmetic I think would be the more accurate, what we call it. But 8 plus 5 is not 13 on a 12-hour clock, right? 8 plus 5, if you added 5 hours, 1, 2, 3, 4, 5, you don't get to 13. You get to 1. Okay? So it's actually not equal to 13. 8 plus 5 is equal to 1 on a 12-hour clock. Okay? On a 12-hour clock, 8 plus 5 is 1. Now that seems kind of weird. In fact, you don't get anything outside of 12 or past 12. And generally speaking, now on our clocks, our standard clocks that we use the number 12. Generally speaking, when we have a 12-hour clock, or if we're doing modular arithmetic with any size clock, it doesn't have to be 12 hours in fact, the last number we don't actually include, we use the number 0 there. Okay, so it'd be 0 on top and 1, 2, 3, all the way around to 11 in this case. So typically I'm going to use a 0 in place of that 12. Okay. So that's not our typical notation when it comes to clocks, but that's what we're going to do when we're talking modular arithmetic here. So 8 plus 5 is no longer 13, it's now 1. So our shorthand for this, because this is confusing to have two different notations and to have to specify like this. So we have a shorthand version. We would say that 8 plus 5 is equal to 1 mod 12. Okay, the mod 12 just means you're looking at a 12-hour clock, or you're looking at a cycle of 12 before you start over again. Okay, so we think of it like a clock, but really you're talking about cycles. It's an endless cycle, in fact, because you go around the clock in, indeterminate amount of time, however many you want, right? Endless number of times. And so this is, instead of having, a lot of times I think of it like, instead of having a number line, right, the real number line that goes from negative infinity on one side to infinity on the other and has all the numbers in between, we're now looking at a number circle. And we chop off the number line somewhere, bend it into a circle, and then you're just going around the circle and endless. It's still an infinite length in some sense. You're just limiting yourself to what your options are. All right. So, obviously this number right here is still the number 13. And so, how do we calculate these things is a question. Especially if my numbers are big. So if I had, let's say, if I wanted to figure out what 68, what is 68 mod 12? Let me write that. What is 68 mod 12? In other words, where would you end if you started at 0 and just went around 68 hours on a 12-hour clock? Where would you end? That's essentially what's being asked here. And so the answer to that question is, first of all, you've got to pull out all of your 12s, right? Every time you go around 12 times, or every time you hit a 12, you start over at 0. So you can essentially divide out all chunks of 12 from that 68, okay? So the nearest multiple of 12 to 68 that's less than 68 is 60, right? So you could take out 60, right? So you get 12, 24, 36, 48, 60, and then you go around 8. 1, 2, 3, 4, 5, 6, 7, 8. And that would get you to 68, right? So 8 o'clock would be the answer to that. So 68 mod 12 is 8. Okay? Now, that's still kind of clunky to have to sit there and count out your 12s, right? So why don't we just divide by 12? Take those out and look at what the remainder is. Okay, it's the same thing, same idea. If you divided 68 by 12, 12 goes into 68 60 times. Oh, no, that does not go into 68 60 times, it goes into 5 times. I'm getting ahead of myself here. 5 times. 5 times 12 is 60. All right. right? Somebody teach me how to do long division, I guess. There we go. And then you subtract to get your remainder. The remainder is 8. So what's neat about clock arithmetic is we have built into our calculation algorithms, I guess, we have a way to calculate modular arithmetic. Essentially, it's the remainder when the number is divided by the size of the clock. Okay. So the remainder will always be the time, so to speak, the answer. All right. So let's say we had a let's say we stick with this clock for a moment, 12-hour clock, and let's say we repeatedly add numbers, the same number together. Okay, so let's say I wanted to add 4, for instance. So let's go 4, well, anything mod 12 that starts out less than 12 is itself. Okay, 4 mod 12 is 4, right? Always starting at 0. And so if I wanted to do 4 plus 4 mod 12, well, that's just going to be 8, right? You go 4 and then you go 4 more, still less than 12. So I don't have to do any division on those. If I did 4 plus 4 plus 4 mod 12, well, here's where the division starts, because what I have here is 12 mod 12, and if you divide 12 by 12, of course, you get a remainder of 0. Okay, which makes sense now. Why we put the 0 there instead of 12. You don't have a remainder of 12, you have a remainder of 0. Now let's go one further. 4 plus 4 plus 4 plus 4 mod 12. Well, this is 16, right? 16 mod 12, if you take 16 divided by 12, again, goes in one time with 4 remainder. So you get 4. And what's going to happen is you're always going to land on 4, 8, 12, 4, 8, 12, 4, 8, 12. No matter how many times you add 4, you're only going to hit 3 different numbers, which is cool. There's nothing wrong with that. That's actually kind of neat. It creates kind of a pattern here. Almost looks like a flower the way I drew it, or petals of leaves of a plant or something. So you have some what we call rotational symmetry. It's kind of interesting. So you have 3 rotations out of 12 that are shown here. Okay. In fact, the rotational symmetry, based upon the degree measures of the angles, this would be a 120 degree rotation, because the whole circle is 360 degrees. That's 1/3 of it, right? So that's 120. So that's kind of neat. You get some rotational symmetry popping out there. And with a 12-hour clock, we get a lot of those symmetries. You could also do the same sort of repetition with the number 6. Right, if you wanted to go with, if you were repeatedly adding 6, you get 6, then 0, then 6, then 0. There's only 2 options there. If you wanted to go with 3, you have 3, 6, 9, 12, 0, 3, 6, 9, 0, and so forth. If you want to go with 2, you have 2, 4, 6, 8, 10, 0. And that's all you would get, right, if you went back around. Well, what about the number 8, or the number 9, or the number 10? Let's try 10. 10's kind of a cool one. Let's start out with 10. Oh, actually, let's rewrite this a little bit. Let's then figure out what are the results when adding 10 over and over again. So 10 mod 12 obviously is 10 because it's less than 12. 10 plus 10 is 20. You can think of it, you get around to 10, then do another 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hit 8. Okay. Then 10 plus 10 plus 10 is 30. 30 mod 12. Take 30 divided by 12. Your biggest chunk of 12 in there is 24. So you pull out the 24, and you'll be left with 6, right? To get from 24 to 30, you need 6 as your remainder. So you'd be at 6. So you get 10 and 8 and 6. If you did 10 plus 10 plus 10 plus 10, that's 40 mod 12. Well, the biggest chunk of 12 is 36. Take the 36 out and you're left with 4 to get up to 40. So we have a remainder of 4 there. And what you'll find is that by adding 10s, you're going to get the same sort of symmetry as with the 2, but in reverse order. Okay, so it's going that way. Oh, that's terrible. What am I doing? Trying to draw something that looks kind of cool so that you can kind of see symmetry popping out. Of course, I'm not keeping those very consistent, am I? But anyway, you get a symmetry with, 6 petals, or 6 different rotations. In other words, if you turn that 1/6 of the circle, again, the circle has 360 degrees, so the angle between any 2 petals is 1/6 of 360, or 60 degrees. Okay, so if you rotate 60 degrees, you get exactly an overlap of that shape. Okay, so that's rotational symmetry popping up in there. Okay, so what's neat is that all of the numbers I just showed as an example, 4, 6, 10, 2, 3, they're not relatively prime to 12. Okay, let's see what happens if I choose a number that is relatively prime. Let's try the number 5 for a moment. And notice up here, there's only 4 numbers relatively prime to 12. 1, 5, 7, and 11. Okay? So let's just see what happens if I were to choose the number 5. We'll just take one of the smaller ones. So 5 plus 12 is, of course, 5 mod 12. 5 plus 5 makes 10. That's less than 12, so that's 10. 5 plus 5 plus 5, well, once you get to 10, you go 5 more. 1, 2, 3, 4, 5. That would be 3, right? And that makes sense because this is 15. 15 mod 12 is, you take out the 12 and you're left with 3 as a remainder. Right? Add another 5 in there. Do this a 4th time. This is 20 mod 12. Well, if you take out 12 from 20, you're left with 8 as a remainder. Okay. And then you add another 5. And really, all I could do is I could just jump up by multiples of 5, right? So instead of writing all of these 5s, which is a little bit tedious, 5, 10, 15, 20, let's do 25 mod 12. Well, you take out, you would take out 24, because that's a multiple of 12, and you'd have 1 as your remainder, right? So think about it as 25 divided by 12, which would be 2, pull out the 24, and you have the remainder of 1. Okay, so again, it's the remainder we're looking for. We jump up another 5, it'd be 30 mod 12. 30 mod 12 would be, if you take out that same 24, you end up with 6. And then if you did 35 mod 12, and notice we haven't repeated anything yet, which is kind of where I'm getting at here. I'll stop when we repeat something. So 5, 10, 3, 8, 1, 6, 35, if I pulled out, I got to pull out 24, and that leaves you with 11, right? That makes sense because you're jumping by 5 here. And then 40 mod 12, you'd have to pull out 36 this time, and 36 would be another 4. And then let's see, 40 mod 12, let's do 45. Still haven't repeated anything. So 45 mod 12. 45 mod 12 would be another 5 onto this, so that'd be 9. Still haven't repeated anything. Go to 50 mod 12. 50, you have to pull out 48. That's the nearest multiple of 12. And that leaves you with 2. Still haven't repeated anything. 55 mod 12. Is, let's see, be 7. You add another 5 to that. 60 mod 12, we've already seen 60 before. That's 0, right? Because that is a multiple of 12 itself. And then you add another 5. 65 mod 12. Obviously, I'm running out of room here. But you'll get up to 5 because you pull out 60, add 5 in, and then you get back to here. So now we've made it all the way around. And then you will end up with the same pattern after that. Okay, so it'll be 5, 10, 3, 8, 1, 6, 11, 4, 9, 2, 7, 0, 5, 10, 3, 8, da 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 da. If you keep adding 5s. What's nice about this is that I hit everything. Notice in here there's a 1, there's a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? That's everything. And so I haven't missed anything. And so that will actually happen anytime that you're working with a number that's relatively prime to the mod number, okay? So because 5 is relatively prime to 12, if you repeatedly add 5, you'll eventually hit everything, right? You get, you start here, you'll get 5, and then you get 10, and then you get 3, and then you get 8, and then you go to 1, and you can kind of see how this is going to develop. And you get 6, and then 11, and then 4, it's just filling in the gaps, and then 9, and then 2, 7, whoa, that was awkwardly large right there. There we go. 7, 0, and then it would start over again. So you can see how everything gets hit. This is a 12. This is a shape with 12 rotations of symmetry here, and so each angle between those petals, each angle is 1/12 of 360, which is a 30-degree angle. Okay, so kind of neat. Some interesting stuff popping out there. Now, I did everything with a 12-hour clock. The size of the clock doesn't matter. Okay, so let's say I wanted to repeat this process or something similar with a different size clock, and we can make it as big or small as we want. I want that circle to stay because I actually drew a decent circle and I don't want to risk messing that up. So I'm going to keep the circle up there as best I can. Okay, so let's say I wanted to work with a clock that was, I don't know, let's go with 5 inside. No, 5's kind of a weird number to use here. Maybe we'll go 9. 9 could work. So I go 0. Now 9, trying to place everything around here evenly will be a little bit strange. 9 is divisible by 3. And so I could do 0, 3, 6, 9, 3, 6, whatever. So 3 would be kind of over here, 6 is over here. So it's kind of like, oh, it looks like a peace symbol. Huh, interesting. Anyway, it's 1/3 of the circle, right? 120 degrees. So 0, 3, 6. And then within each of these gaps, I can fill in with 2 more numbers, right? So I got 1 and 2 in here. So just try to evenly space them out. 4 and 5, 7 and 8. Okay. Apologize for the sump pump noise. The thing's going off like crazy right now. Got a lot of rain the last few days. Anyway, tangent. So got a 9-hour clock, and if that means if I wanted to calculate something like 15 mod 9, then what I'm doing essentially as a visual is starting at 0, and you go around 15 hours, right? A little different, but on this clock, 15 hours on a 9-hour clock, you get around to 9, 10, 11, 12, 13, 14, 15 would be 6. Okay, and again, that makes sense because 6 is the remainder when you divide out the 9, okay, from the 15. If I want to do something like 87 mod 9, now this one I don't want to sit here and count 87 times around. That's ridiculous. I don't really even want to count multiples of 9 till I get to 87. I'm just going to divide, right? It's just a quicker way. 9 goes into 87, 9 times? 9 times 9 is 81. The remainder is, 6. Look at that. Got the same thing. All right. And so we can do calculations this way. We can also then look at patterns with the 9. If I were to repeatedly add a number that was not relatively prime to 9, I'm going to miss something. So for instance, the number 6, right? If I did 6 mod 9, well, that's 6. If I did 6 plus 6 mod 9, that's going to end up being 3, right? That's 12. Take 9 off, you get 3. If I did 6 plus 6 plus 6 mod 9, well, 6, 12, 18. That's equal to 0 because 18 is divisible by 9, okay? So you end up only getting 6, then 3, then 0, and if you continue that pattern around, add another 6 in there, you're just going to get back to 6. So you're just going to get 6, 3, 0. That's all you're going to hit, okay? You're going to skip 1, 2, 4, 5, and 7, and 8. If you were to use a number that is relatively prime to 9, then you'll hit everything, right? So if I use, say, the number 7 mod 9 is 7. 7 plus 7 mod 9 is that's 14. Take out 9 and you get 5, right? And so you can keep making this. If you continue that pattern, you'll get 7, 3, or 7, 5, 3, 1, 8. Then you get 6, then you get 4, then you get 2, and then you get back to 0 again. So you'll eventually hit everything on the list, okay? Just by repeatedly adding 7 in. So because 7 and 9, again, are relatively prime, they only share a factor of 1. When you repeatedly add that 7 in, you'll get everything on the clock eventually. All right. So just some kind of cool ideas. This addition can also be represented slightly different way, and there's a couple problems in your textbook like this. Now your textbook doesn't go very in depth into modular arithmetic. I do have a worksheet posted in e-learning that will cover more of this, give you a little more practice than what the textbook has, so that you get some practice, I guess, more experience with it. So, but your textbook, instead of writing it out as mod 9 every time, your textbook will take this image or this idea and turn it into a symbol. It'll say, okay, for the following problems, use mod 9 whenever this symbol shows up, and it uses a plus with a circle. and it'll tell you for each problem what that's going to be. And then it'll just say, okay, so what is 7 plus 5 mod 9, right? So they circle the plus, and then they're implying that it's going to relate to this modular arithmetic. And so 7 plus 5 mod 9 is going to go, you're going to go around 7, and then 1, 2, 3, 4, 5 around, puts you at 3. So 7 plus 5 in this scenario is just the number 3. Okay, and you don't see the mod 9 written out, even though that's really what you're doing. Okay. You may also see a table form of this. Now, if you think about the comparison of these, if you were to add not just the same digit over and over again, but just try to add, like, okay, if I added 7 and 5, I get 3. If I added 8 and 5, I get 4. If I added 6 and 2, I get 8. What you'll find is that the different combinations give you different values, and there's patterns to the table of the sums. And so you could write out, say you're adding different digits, 0, 1, 2, 3, 4, 5, 6. I'm going to run out of space, aren't I? I really thought I had enough room right there to do this. 0, 1, 2, 3, 4, 5, 6, 7, 8. 9 I do if I write smaller. And then I go down. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then, of course, you have your rows and columns associated with each pair of numbers. So in other words, if I were, let's select the number 4 for a moment. Take the number 4. If I add 0 to it, I get 4. If I add 1, I get 5. If I add 2, I get 6. If I add 3, I get 7. If I add 4, I get 8. If I add 5, I get 0. Because after 8, you get back to 0. Then you add 6, you get 1. Add 7, you get 2. Add 8, you get 3. Add 9, you get 4. Right? And at the end, 9 doesn't make any sense because there's no 9 on the chart. So I don't even need that last column or this last row. It really just goes 0 to 8. Okay? And so you're looking at the sums of the two numbers. The row by the column give you a sum of those two. So for instance, 6 and 4, I already did 6 and 4. Let's do 6 and 5 maybe. Right, so wherever those end up in there. That entry of the table, 6, add 5, 1, 2, 3, 4, 5, it's 2. Right, so that entry of the table will be a 2. And so forth. And you can fill in the whole table this way. And I don't know. So that's something that you'll see in your textbook. In fact, they'll give you the table often rather than the circle and ask you to find the sum. Right, so if I filled out this table and then I said, what is, what is 4 plus 7? Then you would just go to the table and you'd find, aha, that's 2. And so then you don't have to do the calculation. The table kind of has the calculations done for you. Okay. So just a few different ways, of course, you can count on a clock, you can use a predetermined table, or my favorite is use the remainder off of a division to get you the solution to modular arithmetic.